We are going to begin this section by analyzing the limit of functions as x approaches a number in two ways. We're going to do that graphically by looking at the graphs of functions and numerically by looking at tables of values. So first graph that we're going to look at will be the graph of this function, f of x equals sine x over x, around x equals 0. So imagine again, let's go from left to right. X is approaching 0 from the left. As x is approaching 0 from the left, imagine over here, the y value is going to be here. X is getting closer to 0. The y value is increasing and increasing and increasing. So in every case, you notice that as x gets very, very close to 0, I'm going to put an arrow here indicating x is getting closer to 0 from the left. I want you to notice what is happening to the y values. The y values are increasing towards 1. On the other side, something very similar is going to happen. Now, x is approaching 0 from the right. So we are here. That's the y value corresponding to this x value. Then I go over here. The y value is increasing. X is getting smaller, but the y value is getting larger and larger and larger. So then it appears that as x approaches 0 from the right, the y values are going up, up, and up towards 1. So graphically, what we really see is that the limit of the function at 0 seems to be equal to 1. Symbolically, we're going to go ahead and write this as the limit as x approaches 0 of sine x divided by x equals to 1. You remember that we mentioned in the introduction that sometimes we get a little bit lazy and instead of writing the actual expression, we just write f of x. That's totally allowed too. The limit as x approaches 0 of f of x is equal to 1. And something that I want you to notice here is that the function is undefined at 0. Because at 0, for a function like this, we would have f of 0 equals to the sine of 0 divided by 0. Sine of 0 is equal to 0. And as soon as you get something like this right here, you have the indeterminate form. This is saying that there is no value. There's no y value when x is equal to 0. This is actually undefined. So this is why when you look at the graph, you're going to see an open circle right here. However, the function is undefined at 0, but the limit exists. The limit is equal to 1 because, again, emphasizing the limit is a neighborhood concept. You are analyzing what happens around 0, really close to 0. We don't care what happens at 0. The function may not be defined at 0, like in this case. What we care is for the function to be defined slightly on the left of 0 and slightly on the right of 0. And we want to see that the y values are converging to something, just like these arrows are indicating. We want to see that the y values are converging to a fixed real number. And in this case, the y values are converging. Converging means approaching. They are approaching 1. The function is undefined at 0, but the limit is not. The limit exists. The limit is equal to 1. Example 1 says, is asking us to analyze the limit of the following functions graphically and numerically. So let's do the graph first. Let's see what is happening. I notice immediately that at 9, the function is undefined. But I know that even though the function is undefined at 9, the limit can still exist because the limit only cares about what happens as x gets very close to 9 from the left and what happens as x gets very close to 9 from the right. And then I notice that as x approaches 9, from the left of 9, the y values are getting larger and larger and increasing towards 6. And as x approaches 9 from the right, again, I see that the y values are now getting smaller and smaller, but approaching or converging towards 6. So based on the graph, I can conclude that the limit as x approaches 9 of f of x is going to be equal to 6. Now, it is always a good idea to look at the graph also and see what is happening as x approaches 9 from the left. First of all, I want to point out this notation right here. In the next segment of this video, just in a few more minutes, I will carefully explain what this notation means. But right now, just informally, this notation means that x is approaching 9 from the left. This tiny negative means from the left. And here, this is telling us that x is approaching 9 from the right of 9. But again, in a few minutes, I will carefully elaborate on this notation. So let's approach 9 from the left. You can see here 8.9, 8.99, 8.999. Notice how the x values are getting closer and closer to 9. Now let's look at the y values. The y values are 5.98329, 5.99, 5.999. And so clearly, as x approaches 9 from the left of 9, it seems as if indeed the y values are getting closer and closer to 6. On the other side, now the x values, look at them. They're approaching 9 from the right. So for example, 9.1, 9.01, 001, and so forth. So if you now focus on the y values, you're going to see 6.01, but then the next y value over here gets smaller, 6.001, and even smaller, 6.001. So then again, it seems as if our conclusion from here is accurate. The limit of this function at 9 is indeed equal to 6, even though the function is not defined at 9. If we look at b, now they're talking about the limit, and the function here is x squared as x approaches 4. So if we look at 4, now I have a heavy dot at x equals 4. This is telling me that this function is defined at 4. Fantastic. The limit doesn't care. The function can be defined or undefined at 4. I care about what happens around 4. And around 4, let's go from the left of 4 again. So in this direction, if you notice, the function is increasing towards 16. And on the right of 4, the y values are decreasing towards 16. So from the graph, it seems as if the limit as x approaches 4 of x squared is equal to 16. But let's look at the analysis numerically. Let's look at the graph. Again, on the left of 4, look at the x values. They're getting closer and closer to 4. So 3.9, 3.99, and so forth. If we look at the y values, they're clearly getting closer and closer towards 16. And on the right of 4, 4.1, 4.01, the x values are getting closer and closer to 4 from the right of 4. If I look at the y values are approaching 16. So we feel that this conclusion is quite accurate. Both the graph and the table are showing that the limit of the function at 4 is equal to 16. this graph is actually quite interesting. This is the graph of sine of pi over x. If you look at the behavior, the graph seems to oscillate back and forth between 1 and -1. Even though it's not shown here, this maximum value is +1 and this minimum value is -1. So we have this oscillation, literally like this, up and down, up and down, up and down, around 0. And this is where the limit is going towards. This is the limit as x approaches 0. So the question is, what is that limit equal to? Does it equal to something? Does that limit exist? And because of this oscillating behavior, up and down, up and down, up and down, around 0, this graph is pretty much telling us that the limit at 0 of this function does not exist. This function has no limit at 0. So the conclusion will have to be that the limit as x approaches 0 of sine of pi over x does not exist. Doesn't exist. There is absolutely no limit at 0. If we look at the table, on the left of 0, look at the x values that were chosen, -0.1, -0.03, -0.007. So those x values are getting closer and closer to 0. And if you now observe the y values, look at this. We don't see that the values are approaching something like a real number. You don't see this behavior like in the previous two examples. If you notice, when x is -0.1, the y value is 0. And then x is getting closer to 0, but the y value now goes all the way to 0.866. X is getting closer to 0, right? Now x here is -0.007. Look at the y value. Now the y value goes all the way negative below the x-axis, -0.434. Then as x gets closer to 0, the y value jumps all the way up to 0.342. And then x is getting closer to 0. The y value goes all the way down, pretty close to -1, so -0.935. So clearly, we're not seeing this convergence, this approaching feature that we were seeing in the previous examples. If you now look at what is happening to the right of 0, again, the x values are getting closer and closer to 0. But look at the y values. They keep jumping up and down, up and down. There's no converging factor here as well. So indeed, even the table is concluding the same thing, that this function has no limit at 0. I want to now caution you about something when it comes to tables. Tables can be a little bit tricky. If you remember, in the previous examples, I believe that one of the limits was approaching, x was approaching 9, right? So here was 9, and we were analyzing x values on the left of 9 and x values on the right of 9. And I believe that we chose x values starting with 8.9, then 8.99, 8.999. So somehow this behavior, this pattern is really what I think of as well-behaved. We just keep adding 9s after the decimal, 0.9, 0.99, 0.999. And on the right, we took x values starting with 9.1, 9.01, 9.001, and so forth. And this was good enough for us to see what the y values were approaching. That was in one of the previous examples that we just finished discussing. If you notice right here on this table, the x values that were chosen were not as well behaved as this one. They're completely random. There's no pattern here. negative 0.1, negative 0.03. They didn't say negative 0.01, negative 0.001. So why? Why was this done in this way? Imagine that instead of choosing 0.1 and then 0.03 and 0.07, I would have continued with the pattern of 0.1s. This is what I mean. I know that sounded complicated. Let's say, again, I am assuming that these are x values. So in this case, we end up getting x is equal to 0.1. I'm going to keep that the same. And then x equals to 0.01. X equals to 0.001. And let's do one more. X equals 0.0001. Let's say that I would have chosen those x values. Clearly, these values are getting closer and closer to 0 from the right of 0. So what I'm going to do now is change this to fractions. This would be 1 over 10. This will be 1 over 100, 1 over 1,000, and 1 over 10,000. So something like this. Now, what would the y values be? So this is now y. So y would be, for this one here, would be sine of pi divided by 1 over 10. That will give me sine of 10 pi, and this will give you 0. Similarly, if I do this one here, the second one, this will be sine of pi over 1 over 100. That will be sine of 100 pi. That will give me 0. And in the same way, if I do this one here and this one, I am going to get 0 and 0. So erroneously, we would have concluded that the limit exists at 0 and that is equal to 0. So this is one of the deficiencies of tables. While tables can be very helpful to determine the limit of a function at a particular value of a, they can also at times be very misleading. So if we choose x values that follow a pattern like this, 0.1, 0.01, 0.001, with this function, we can conclude that the function has a limit at 0, when in fact the function doesn't have a limit at 0. So this is why every now and then it's good to shake the values up a little and just make sure that you choose random x values that are getting closer to a, whatever a is equal to, but without sometimes following a clear pattern just by inserting zeros, for instance. So this is why in this table, the x values are getting close to 0, but in a very random way. Because if we were to do something similar here, as in the previous examples, we would conclude that the function has a limit. So in general, as an advice, whenever you have a trigonometric function and you're trying to analyze the limit of that function numerically, my advice would be to try to choose x values that are not so predictable as these ones right here. Again, the x values, they have to be approaching a, but they don't have to be approaching a in a predictable way, like in this case by just adding zeros between the decimal point and 1. So they're a little bit more random. That will be my advice with trigonometric functions. This is now the last example. They're asking us to find the limit as x approaches 0 of this function right here. Let me mark that down, that this entire expression is f of x. I want you to notice as well that I didn't give you a graph. So we're going to base our conclusion from a numerical perspective. We're just going to be analyzing the tables. The table above consists of x values that are bigger than 0. They are towards the right of 0, but they are getting closer and closer to 0. Again, I noticed that this function involves a trigonometric function. I have cosine of 5x. So to avoid any misleading answer, any confusing answer, I went and I chose x values that approach 0 from the right, but they seem a bit more random. I started with 1, then 0.5, then 0.1. I didn't go 0.05, 0.005, 0.0005, because with trig functions, we have to be a little bit more careful to avoid any answer that is inaccurate. So 0.1, 0.05, 0.01, 0.005, 0.001. So all of these values over here are approaching 0 from the right of 0. They're getting smaller and smaller, but in a more random manner. Now let's look at the y values. And again, this is done with the calculator. If we start with x equals 1, this is the y value that was generated. 0.5, this is now the y value. And if I now go down the list, actually, if I just go up to here, it kind of seems, imagine that I only consider these values, it seems as if the limit is approaching 0, right? Because I end up getting 0.000222, 0.000101. But if I continue a little bit more with the table below, I now see a clear pattern that the y values are really approaching 0.0001, 0.0001. And then these digits over here are pretty much going towards 0. So it will be more accurate to conclude that the limit as x approaches 0 of f of x, again this function right here, is going to be equal to 0.0001. In other words, that will be 1 over 10,000. Okay, so then this seems to be the value of the limit. Example E is asking us to consider this piecewise function here, g of x. We notice that when x is not equal to 1, g of x is equal to x plus 1. It's just linear. You can see the graph right here. But when x is equal to 1, the y value is not 2 because we are no longer on the line. The y value is just randomly pi. So this is why you see this dot floating around. This is about 3.14, exactly an approximation for pi. The question is asking, does the limit as x approaches 1 of g of x exist? Yes or no? So then we have to remember, and we already went over this quite a bit, that the function doesn't have to be defined at 1 and the limit can still exist. And in this case, actually, the function is defined at 1. In fact, it is defined at 1. When x is equal to 1, the y value is pi, meaning that the y value is not on the line, is a little bit above the line. So the limit, however, is interested in what happens around 1. And around 1, let's say in a small neighborhood, around 1, as x approaches 1 from the left and as x approaches 1 from the right, see what is happening to the graph. I am on the line. And it seems as if the y values are approaching 2. Similarly here, for this x value, that's the y value, now the y values again are going towards, they're going down towards 2. So on the left of 1, we're climbing towards 2, and on the right of 1, we are descending towards 2. we don't care that at 1, the y value is pi. We don't care about that. We notice that close to 1 on the left and on the right, the y values are approaching 2. So therefore, that becomes the limit. So we conclude here that the limit as x approaches 1 of g of x is going to be equal to 2. And remember, 2 is not the y value. 2 is not equal to g of 1. Doesn't matter. The limit has to do with what happens around 1. And around 1, the y values are converging towards 2. Now we're going to go ahead and construct a formal definition of a limit, something that captures pretty much everything that we have said over and over again since we started this video. For example, why don't we start in the following way? Suppose that f of x is a function and a is a real number. A can be any real number. The limit of f of x as x approaches a, and this is exactly what we are trying to define right here, the limit. The limit as x approaches, the limit of f of x as x approaches a is a number L such that the following is true. For L to be the limit, that means that as x approaches a from the left and from the right of a, of the number a, then f of x approaches the number L. That same idea that we have been trying to capture since the beginning of the video. So, for example, let's go ahead and have a visual. Think of this as the x-axis. You're going to think of this as the y-axis. And let's say that we position A right here. Let's say that this is that number L. This is the x-axis. This is the y-axis. So then what we are saying is the following. We're saying that if this number L is going to be the limit of this function, then as x approaches a from the left and from the right, the y values here on the y-axis, they have to be approaching L. So if x is getting really, really close to a, the y values are really getting closer and closer to L. That's what it means for something to be a limit. So symbolically, we write that the limit as x approaches a of f of x is equal to L. Repeating again, as x approaches a from the left and from the right, the y values of the function are getting closer and closer to L. And remember that the function may not be defined at a. What is important is for the function to be defined around a and for the y values to be converging, approaching the same number L. If that happens, then L is the limit of the function at x equals a. Before we move on, there are two limits of two functions that I want us to establish right now. And I want you to think of creating a toolbox for evaluating limits. And the first two tools that are going to go in that box will be the limit of a constant function and the limit of a basic line, the line described by y equals x. This is the line that passes through the origin at a 45-degree angle. So what are those limits? So here I have a random a. A can be positive, a can be negative. It doesn't matter. And here I have a constant function, y equals c. And again, c can be above the x-axis, c can be below the x-axis, is irrelevant. So then what I want us to investigate here is what is going to be the limit as x approaches a of the function f of x. But please remember, f of x is equal to c. So then here I am going to write c right there. So what is that limit? I want you to notice that the analysis is going to be the same as before. For example, as x is getting closer and closer to a from the left, the y values, let me go up to the graph, are always at a height of c. So the y values are equal to c. Similarly, as x approaches a from the right, the y values are equal to c. So no matter what, as x gets very, very close to a, the y values are always c. So therefore, the limit of this function is going to be c. So for example, if the constant function is y equals 3, and they ask me, what is the limit as x approaches 4 of the function 3? Try to imagine that. Then I know that because the y values are always 3, regardless of what x is equal to, then the limit is going to be 3. If the function is y equals -5, and the question is, find the limit as x approaches -2 of the function -5, then again, imagine that I draw a tiny diagram here. Here is my x-axis, my y-axis here, and y equals -5, that is going to be somewhere here. This is y equals -5, and x equals -2 right here. So the idea is as x approaches -2 from the left and x approaches -2 from the right, I want you to think of the y values. The y values are always going to be -5. So therefore, the answer will be -5. And that's always the case. Now, what happens in a situation like this line? Y equals x. The argument is identical. As x approaches a from the left, look at the y values. The y values are approaching f of a. And f of a is a, because this is the line y equals x. And then on the other side, so let's say that I choose an x value right here. I'm going to go up to the graph, and again, I seem to be approaching a. So I approach a from the right of a, and I approach a from the left of a. So this is exactly the limit here. So then that means that indeed, the limit as x approaches a from the left and from the right is always going to be equal to a. So then, the limit as x approaches a of the function f of x, here f of x is equal to x, is going to be equal to a. So if, let's say, again, I'm dealing with the function y equals x, and they ask, well, what is the limit as x approaches 4 of x? Then I know that immediately the limit is going to be equal to 4. Again, my graph is y equals x, and somebody asks, what is the limit as x approaches -3 of x? then I know that the limit is going to be -3. If I go up to the graph, let's say that this is -1, -2, -3 right here. And then I analyze the limit as x approaches -3 from the left. I'm going to go down to my graph, and I keep the y values are increasing, and eventually those y values are reaching -3. Then on the other right, I'm approaching -3 from the right of 3. So I am moving towards -3 from the right. Look at the y values. They are still approaching this point right here, which happens to be at -3 as well. So these are two limits that I want you from now on to always remember, that if the function is constant, then the limit as x approaches any a is always equal to the value of the constant. And if the function is the line y equals x, then as x approaches a, the limit is always a, because the y values of the function are getting closer and closer to a. So this is another result that I really want you to keep in mind from now on. The limit as x approaches a of the line y equals x is always a, and given a constant function, the limit as x approaches a of the constant function is always equal to c, whatever that constant is equal to. So two very important limits. Let's please keep that in mind and try not to forget. From now on, you can always assume that this is always true.